All right, today we're looking at lesson 50. We're dealing with vibrating systems. So hopefully after this lesson you'll understand vibrating systems. If an object that's displaced from its equilibrium position is always subjected to a restoring force that tends to return the object to its equilibrium position, the resulting motion is called a vibration or an oscillation. So if you have an object and you move it and it pretty much always returns to its equilibrium position, that's going to give you a vibration or an oscillation. Simple harmonic motion is a common and an important kind of oscillatory motion that occurs if the restoring force is proportional to the displacement of the object from its equilibrium position. So this condition is approximately satisfied by the motion of a spring mass system, especially if your displacement from the equilibrium is a very small amount. So if you look at these pictures, the mass in the system rests on a frictionless surface, and when displaced from equilibrium, it'll move back and forth on either side of the equilibrium position. And the wheels attached to the mass are present because this is a method that the book will use to approximate a frictionless surface in an experiment. So it makes it so that it's almost frictionless. The wheels in our diagram are massless, frictionless, and play no part in the solution of the problem, but they help to make it clear that the mass is free to move along the surface. And so we don't have any friction or anything like that. And so for this reason, most of our masses will have wheels. So in the figure on the left, this one right here, we show a mass that's attached to a frictionless spring, and it's neither stretched nor compressed. So this position right here is equilibrium. On the right side, we stretch the spring, we pull it back from the equilibrium position, and the energy that is stored in the spring is 1/2 Ka squared. K is our spring constant, and then A is our distance, and that's the distance that it was moved. The energy, or the object, has been displaced a distance of A in the positive X direction, so the restoring force is going to be negative Ka. So our force is going to be negative Ka. That's the restoring force. And so the minus sign tells you that the force acts to the left in the direction opposite of the displacement, because we're going to have to go back to the left to make it go to where it needs to be for the equilibrium position. And if we plug it into Newton's second law, F equals ma, our F is negative Ka, and that has to equal ma. And so the acceleration is going to have to be a negative. Your mass is not a negative number, so this acceleration is going to have to be a negative because it's going to be to the left, which is in the direction opposite of the displacement. Then this figure here, the bottom left one, it's going past the equilibrium position with a speed of v. All of the spring's potential energy was converted into kinetic energy. And then on the figure on the right, it got compressed as far as it'll go, and now it's going to go back the other direction. And it's going to oscillate back and forth until eventually it comes to rest at the equilibrium position. Okay? So the energy that's stored in the spring is going to cause the object to accelerate to the right. And since no energy is lost to friction, the object will go back and forth forever. And so, of course, all of your objects, all of your springs in real life heat up under repeated movement. And so they lose energy to heat. So in real life, all of your springs, they're not perfect springs. But we're going to let the springs in our problems be perfect springs to allow us to practice working with the concept of energy transfer. So in real life, if you did this, eventually your springs would not go back to equilibrium position. They'd get stretched out or compressed more. But in our examples, we're going to be dealing with perfect springs. So the energy of the system at any instance is going to equal the sum of the kinetic energy and the potential energy, and this sum will be constant for a frictionless system. So they're trying to make it a little bit easier for us. So let's look at an example. We've got a perfect spring whose spring constant is 1500 newtons per meter, and it's attached to a 1 kilogram mass that slides on a frictionless surface as shown. The object is moved 20 centimeters from its rest position and released. What will be the speed when it passes its rest position? We are going to use the fact that our potential energy is going to be 1/2 k and then the distance squared. Okay, so our k is our spring constant, which they told us was 1500, and the distance is 20 centimeters, so 0.2 meters. You don't really need that zero there. 0.2 meters squared. And so if you solve that, you'll get 30. So whenever the mass passes the rest position, all of the potential energy is going to be converted to kinetic energy. So your potential energy is going to equal your kinetic energy. And our kinetic energy formula is 1/2 mv squared. So we know that that's going to be 30. Then we have 1/2. Our mass is 1, and then we're looking for our velocity. So our velocity squared is going to be 60. So take the square root of that, and your velocity is 7.75, which we only have one sig fig here and here. So our velocity would be 8, and then units, meters per second. So that would be how you would work through that problem. Let's look at another one. We've got a mass of 3 kilograms attached to a perfect spring whose spring constant is 2.00 times 10 to the third newtons per meter. The spring is stretched and released. If 450 joules of energy was added to the system when the spring was stretched, what will be the speed of the mass when it is 10.0 meters from its rest position? So we know that the total energy of our system is going to be the potential energy plus the kinetic energy. So our potential energy plus our kinetic energy. And our total energy is going to be 450 because that's what was added to the system when the spring was stretched. So those two have to add up to 450. So our potential energy is the 1/2 kx squared, and our kinetic energy is the 1/2 mv squared. All right, so our K is our constant, our spring constant, which they said was 2 times 10 to the third. And so I'm going to go ahead and convert that to standard, so 2,000. Our distance that was released is 10, and so we're going to convert that to meters, so 0.1. Then we're going to square that. And then we have 1/2. Our mass is 3. And then we don't know the speed. We're looking for the velocity. So you would have 450. And then when you multiply this, you're going to end up getting 10. And then plus 1.5 v squared. So 440 equals 1.5 v squared. If you solve that for your v, you get 17.13. We have 3 sig figs everywhere, so that's going to go to 17.1, and then the units are meters per second. Okay, so that's how you would work through that one. Looking at the next example, it's talking about the last one. What was the amplitude of the vibration? The amplitude is the max distance of the object from its rest position. So when is all of the energy as the potential energy? So that would be when, like, what was the furthest it was stretched out. So 1/2 kx squared. And so we know that we had this much energy. Our spring constant was 2,000, and we want to know how far was it actually stretched to give it that much potential energy. And so if you solve for your x, you should get 0.671 meters. And so that would be the amplitude of the vibration. That's how far out it was stretched. So now you know how your sinusoids, you have your amplitude is from here to here or from here to here. On this one, we're on a flat surface. And so this is the center line, the equilibrium point, and it went out to here and then went back and it oscillated back and forth, except you don't see it. It just looks like it's moving, you know, back and forth, left to right. But if you looked at it as kind of like a sinusoid, the amplitude is the distance from here out to here. And so that's how far it got stretched before it was released. Hopefully that makes a little bit of sense there. Okay, your homework is 1 through 20, and then make sure to look at the curveball questions 1 through 5. So do those tonight, and we'll go over any questions you have tomorrow.